Some of history's greatest scientific ideas were once laughed out of the room. This video explores 25 abandoned space theories that may have been right all along. You are about to discover how yesterday's rejected concepts are quietly reshaping modern astronomy. We will uncover why scientists once believed in a planet called Vulcan that did not exist, and how the search for Martian canals accidentally launched the science of astrobiology. By the end, you will see the entire history of cosmic discovery in a startling new light, where being wrong is often the first step toward being right. How many of today's wildest ideas might be proven true in the future? The most intuitive truth for thousands of years was that Earth stood motionless at the center of everything. This geocentric universe, meticulously mapped by philosophers like Ptolemy, was not a simple guess. It was a brilliant, complex system of circles within circles, designed to predict the wanderings of planets with astonishing accuracy for its time. We rightly celebrate the revolution that dethroned Earth from the cosmic center, yet in our rush to label the old model as simply wrong, we may have discarded one of its most profound, hidden truths. Every observation we have ever made, from a caveman looking up at the stars to the Hubble Space Telescope peering into the deep field, has been made from a single, specific location. That location is here. Our entire view of the cosmos is, and always will be, geocentric in the most literal sense. This is not a scientific inaccuracy, but a philosophical reality. Our instruments do not measure the universe from some abstract, godlike perspective outside of it. They measure it from our own backyard. This fundamental constraint of our viewpoint finds startling echoes in modern physics. Einstein's theory of relativity teaches us that all motion is relative to the observer's frame of reference. There is no single, privileged stage upon which the cosmic drama unfolds. In a way, every point in the universe can be considered its own center. Meanwhile, certain interpretations of quantum mechanics suggest that the act of observation itself plays a role in shaping reality. The geocentric model was ultimately a map of how the universe appears to us, not how it truly is, and that distinction is everything. Its greatest legacy is the humbling reminder that our maps are always drawn from a particular point of view, a lesson that resonates powerfully today as we attempt to map the invisible dark matter holding galaxies together or comprehend the true nature of the Big Bang. Centuries before we understood nuclear fusion, another idea sought to explain the fire in the heavens. It was called the Phlogiston theory, and for over 100 years, it was the dominant explanation for why things burn. Philosophers believed that within any combustible material resided a fire-like element, a substance named phlogiston. When wood burned or a metal rusted, it was thought to be releasing its stored phlogiston into the air. This logic was naturally extended to the stars themselves. The sun and all the stars in the night sky were simply immense, slow-burning spheres, releasing their phlogiston to produce light and heat. It was a beautifully simple and completely wrong answer. The theory collapsed when chemists realized that burning actually involved consuming something from the air, which we now call oxygen, rather than releasing a mysterious substance into it. The phlogiston theory was tossed into the dustbin of scientific history, a cautionary tale of misguided thinking. Yet, to dismiss it entirely is to miss its profound, hidden contribution. The core intellectual framework, the idea that a hidden reservoir within matter could be unlocked to produce energy, was a crucial stepping stone. It primed the scientific mind to think in terms of energy transformation. When the true source of stellar power was finally discovered, it was not a fire-like element, but the unimaginable power of nuclear fusion. Deep in the cores of stars, atoms of hydrogen are crushed together under immense pressure and heat, fusing into helium and releasing a torrent of energy in the process. This process, stellar nucleosynthesis, is the true engine of starlight. In a strange and poetic way, Phlogiston was a placeholder for the concept of mass energy itself, a shadow on the cave wall pointing toward the reality of E equals mc squared. The theory itself was a dead end, but the path of inquiry it started, the search for that hidden source of power, led directly to the revolutionary discoveries of modern astrophysics. It stands as a powerful monument to the fact that in science, even our most elegant mistakes can light the way forward. The search for that hidden source of power was a quest to understand the very fabric of reality. But what is that fabric made of? For centuries, the most brilliant minds in physics were certain that light, like sound, needed a medium to travel through. They called this invisible, all-pervading substance the luminiferous ether. It was thought to be an ethereal sea, filling the emptiness of space, a necessary stage for the cosmic dance of light waves. This was not a fringe idea. It was the cornerstone of classical physics, a framework used by giants like James Clerk Maxwell as he formulated his elegant equations describing electromagnetism. The ether had to exist, but then, in the late 19th century, two scientists, Albert Michelson and Edward Morley, designed an exquisitely sensitive experiment to detect it. They reasoned that as Earth moved through this stationary ether sea, it should create a detectable ether wind, subtly altering the speed of light measured in different directions. Their apparatus was a masterpiece of precision, capable of measuring shifts smaller than the width of an atom. Yet when they performed the experiment, they found nothing. No wind, no drift, no ether. The result was a profound shock to the scientific community, a null result that shattered a fundamental pillar of their understanding of the universe. The luminiferous ether was declared a beautiful, failed hypothesis, and physics moved on, but the ghost of the ether never truly left the building. The conceptual need for a medium, for a something that gives structure to the void, was simply too powerful to vanish. Today, we no longer speak of a material ether, but we describe the vacuum of space as anything but empty. The quantum vacuum is a seething, bubbling foam of virtual particles flickering in and out of existence. The Higgs field is an invisible energy field that permeates all of space, imparting mass to fundamental particles. These are not the rigid, mechanical ether of the 19th century, but they fulfill a similar conceptual role. They are the dynamic, structured entities that allow the universe to function as it does. The abandonment of the luminiferous ether was a necessary death, but from its ashes rose a far stranger and more wondrous understanding of the stage upon which reality is performed. That 19th century quest for a cosmic medium found a strange parallel on our closest planetary neighbor. Mars, the red planet, became the focus of an even more dramatic human projection. Through the eyepieces of powerful new telescopes, astronomers like Percival Lowell saw something astonishing. The Martian surface appeared etched with a vast geometric network of straight lines, a global system of what could only be artificial canals. Lowell passionately argued these were the work of a desperate, intelligent civilization, building colossal waterways to channel water from the polar ice caps to their arid, dying cities. The public imagination was set ablaze. For the first time, the possibility of intelligent life next door felt not just plausible, but observable. The idea of a Martian civilization, fighting for survival on a world older than our own, became a powerful cultural force, inspiring everything from scientific speculation to science fiction. Yet, as our technology improved, the canals began to vanish. higher-resolution telescopes and eventually spacecraft visiting Mars revealed the truth. There were no artificial channels. The lines were a perfect storm of optical illusion, the human brain's natural tendency to connect faint, disparate patches of dark albedo features into straight lines across the vast, blurry distance. Lowell had been profoundly wrong, but was the entire endeavor a failure? The legacy of the Martian canal theory is far more complex than a simple debunking. Lowell's grand, mistaken vision forced science to take the idea of extraterrestrial intelligence seriously. It shifted the question from a philosophical maybe to a potential observational science. The core concept he championed, that an advanced species might alter its planet on a global scale, is now a cornerstone of modern astrobiology. We no longer search for canals, but we actively search for technosignatures, the detectable signs of technology, like artificial atmospheric gases or structured light from distant megastructures. Lowell's era, born of ambition and limited data, ultimately cleared the intellectual ground for a new, more sophisticated field of inquiry. It taught us that our deepest cosmic questions are worth asking, even when our first answers turn out to be illusions. The conviction that the cosmos was eternal and unchanging was once as fundamental as the ground beneath our feet. This static universe model was the default assumption for centuries, a serene backdrop of fixed stars against which the planets performed their slow, predictable dances. Even Albert Einstein, when he formulated his theory of general relativity, found his equations pointing toward a dynamic cosmos, one that was either expanding or contracting. Unwilling to contradict the established wisdom of a static universe, he made what he would later call his greatest blunder. He introduced a fudge factor, a mathematical counterbalance he named the cosmological constant. This artificial force, a kind of repulsive gravity, was designed to hold the universe perfectly still, propping up a model that felt intuitively true. For a short while, the static universe seemed secure. Then came Edwin Hubble. Peering through the Great Telescope at Mount Wilson, he made a discovery that shattered the serene cosmic picture. He found that the distant galaxies were not standing still. They were all rushing away from us, their light stretched into redder wavelengths, with the most distant ones fleeing the fastest. The universe was not static. It was exploding outward from a primordial beginning. The cosmological constant, a fix for a problem that did not exist, was promptly discarded, and Einstein's blunder became a legendary cautionary tale. The universe was dynamic, and the static model was relegated to the history books, but the story was not over. Decades later, astronomers studying the most distant stellar explosions, supernova, made an even more baffling discovery. They found that the universe's expansion was not slowing down, as everyone expected from the pull of gravity. It was speeding up. Some mysterious, repulsive force was pushing galaxies apart at an ever-increasing rate. Scientists needed an explanation, and they found it lurking in the discarded equations of the past. The cosmological constant was resurrected. It was no longer a mistake, but a prophetic insight. It became the leading candidate for what we now call dark energy, the enigmatic force driving the cosmic acceleration. The static universe model was wrong, but its ghost, in the form of Einstein's constant, returned to solve a mystery its original proponents could never have imagined. This journey from abandonment to redemption is a profound lesson in the humility of science. It shows us that our greatest errors are not always dead ends. Sometimes they are simply ideas waiting for their moment, preserved in the archives of our curiosity, ready to illuminate a darkness we have not yet even perceived. The same human impulse that mapped canals on Mars also gazed inward, dreaming of worlds within our own world. For centuries, the idea that Earth might be hollow captivated scientists and storytellers alike. Renowned astronomer Edmund Halley of comet fame proposed a hollow Earth model to explain strange magnetic compass fluctuations. He envisioned a series of concentric shells spinning inside our planet, each with its own atmosphere and possibly even lit by luminous gases, a hidden sun at the core. This was not mere fantasy, but a serious scientific hypothesis that attempted to explain observable phenomena. The concept was later extended to our moon, with some suggesting it too was a hollow sphere, a cosmic egg holding secrets within. We now know from seismic data and our understanding of planetary formation that Earth and the Moon are not hollow. The immense pressures and densities deep within are utterly incompatible with such vast, empty interiors. Yet the poetic heart of this abandoned theory did not die. It simply migrated. Instead of looking for giant caverns lit by inner suns, our probes now search for something just as wondrous: hidden oceans. We have strong evidence that Jupiter's moon Europa harbors a global, salty ocean beneath its icy crust, kept liquid by the gravitational tug of war of its giant planet. Saturn's moon Enceladus actively spews water vapor and organic molecules from its subsurface sea into space. These are not the cavernous, habitable worlds of early speculation, but they are vast, dark, liquid environments shielded from the harshness of space, places where the chemistry for life might just be taking place. The hollow Earth theory was wrong in its specifics, but it was profoundly right in its spirit. It correctly anticipated that celestial bodies could hold astonishing hidden realities, entire worlds concealed from our direct view. The dream of an inner world was abandoned, only to be reborn as the scientific hunt for subsurface oceans, proving that sometimes our wildest imaginings are not failures of logic, but premonitions of a truth far stranger than we could have conceived. Sometimes the universe sends us a puzzle wrapped in an error. In the mid-19th century, the planet Mercury presented astronomers with a stubborn mystery. Its orbit was misbehaving. The point of its closest approach to the Sun, called its perihelion, was slowly drifting around the star in a way that Newton's law of universal gravitation could not fully explain. The math was off, and for scientists who believed the solar system was a perfectly tuned clockwork, this was an intolerable glitch. The most elegant solution seemed to be the existence of an unseen world. French mathematician Urbain Le Verrier, who had famously predicted the position of Neptune, turned his calculations to this new problem. He concluded that the gravitational pull must be coming from a small planet, one orbiting even closer to the Sun than Mercury. He named this hypothetical world Vulcan. The announcement triggered a decades-long hunt. Amateur and professional astronomers alike scanned the skies near the blinding solar disk, especially during solar eclipses. Several reputable observers reported sightings, each one seeming to confirm Vulcan's existence, but the evidence was always fleeting and contradictory. The planet refused to be pinned down, appearing as a ghost in the data, a celestial will-o'-the-wisp that vanished upon closer inspection. The search for Vulcan was ultimately a noble failure. The planet was not there. The solution to Mercury's wandering orbit would not come from a new world, but from a radical rethinking of the very fabric of space and time. Albert Einstein's theory of general relativity provided the true answer. The Sun's immense mass, according to the theory, warps the space around it. Mercury, traveling through this curved spacetime on its tight orbit, follows a path that naturally includes that slow drift. The math of relativity predicted the anomaly with perfect precision, a stunning triumph that rendered Vulcan obsolete. So why does this failed hypothesis matter? The quest for Vulcan was a classic case of being brilliantly wrong for all the right reasons. astronomers had correctly identified a genuine flaw in their understanding of the cosmos. Their proposed solution was incorrect, but their insistence that something was amiss kept the problem alive and urgent. The decades spent scrutinizing the inner solar system honed observational techniques and demonstrated a deep commitment to the scientific principle that every anomaly must be explained. The ghost of the missing planet Vulcan did not point toward a new world, but toward a new physics. It was a dead end on the map that forced us to realize the map itself was wrong. This is the hidden value of an abandoned theory, a wrong turn that illuminates the true path forward, pushing us toward a revelation far grander than anyone had imagined. While astronomers chased the ghost of Vulcan, a far more unorthodox idea was taking root, one that saw the entire cosmos through a frozen lens. The cosmic ice theory, or Weltallehre, proposed a universe built not on fire or ether but on ice. Its proponents, like the Austrian engineer Hans Herberger, envisioned a dramatic cosmology where ice moons collided with primordial planets, and cosmic ice was the fundamental building block of everything. This was not just a theory of the heavens, it was a sweeping narrative that wove together planetary geology, ancient mythology, and even the rise and fall of human civilizations. The scientific establishment rightly dismissed Weltallehre as pseudoscience, a fantastical story built on a foundation of imagination rather than evidence. Its grand claims of ice shaping human destiny were unsupported, and its methods were a chaotic mix of selective observation and myth. Yet, buried deep within this frozen fantasy was a single prophetic grain of truth. The theory was obsessed with the cosmic importance of water ice, and on that one point, it was accidentally and spectacularly right. For centuries, we pictured the moon as a dry, dusty desert and Mars as a barren rustscape. But our modern probes have revealed a solar system rich with frozen water. We have found vast sheets of water ice hiding in the permanently shadowed craters at the lunar poles. We have uncovered glaciers of water ice buried just under the red sands of Mars. Comets, those ancient wanderers, are literally dirty snowballs, carrying pristine ice from the solar system's infancy. The wild speculation of the cosmic ice theorists, for all its flaws, correctly identified ice as a key cosmic material. Today, planetary scientists do not see ice as a mythological force, but as a crucial resource. Water ice can be split into hydrogen and oxygen, the very components of rocket fuel and breathable air, making it the oil of future space exploration. More profoundly, wherever we find liquid water, or the ice that can melt into it, we find a potential cradle for life. The search for life on Europa and Enceladus is fundamentally a search for liquid water made possible by their icy shells. The cosmic ice theory was wrong in its sweeping conclusions, but its core fixation on ice as a central player in the cosmic drama was a strange premonition of what we now know to be true. It serves as a reminder that even the most discredited ideas can sometimes point, however clumsily, toward a real and significant piece of the puzzle. That same impulse to find life in the cosmos once took a much more immediate form. Before we understood the intricate dance of cells and DNA, it seemed perfectly reasonable that life could simply spring into being from non-living matter. This was the doctrine of spontaneous generation. People believed that maggots emerged spontaneously from rotting meat, or that mice could be generated from piles of grain. It was a logical, if flawed, conclusion drawn from simple observation, and when philosophers looked upward, they naturally extended this idea to a cosmic scale. Perhaps the very ether of space was a fertile medium, a celestial broth from which living things could constantly be generated, seeding the universe with life. It was a grand, animating vision of a living cosmos. Then came Louis Pasteur, his elegant experiments in the 19th century with his swan neck flasks that kept dust and microbes out, delivered a decisive blow. He demonstrated that life comes from pre-existing life. The theory of spontaneous generation on Earth was conclusively disproven, and with it, the idea of life spontaneously bubbling out of the cosmic ether seemed to vanish into the realm of superstition. But the core mystery it tried to address never went away. If life only comes from life, then where did the very first life come from? This is the profound question of abiogenesis, the study of how life initially arose from non-living chemistry. And here, the old idea finds a stunning modern echo. While we no longer believe in mice appearing from hay or life forming in the void, scientists now actively investigate how, under the right conditions, the simple molecules present on the early Earth could have assembled into the complex building blocks of life. Experiments have shown that amino acids, the Lego bricks of proteins, can form spontaneously in conditions that simulate a primordial planet. The abandoned theory was wrong about the mechanism, but it was asking the right fundamental question. Even more remarkably, the cosmic aspect of the idea has been resurrected in the form of panspermia. This hypothesis suggests that the basic ingredients for life, or even dormant microbes themselves, could be transported across space, hitchhiking on comets or asteroids. A meteorite from Mars landing in a primordial Earth ocean could have delivered the spark that started it all. We are not suggesting life forms in the ether, but we are seriously considering that the seeds of life can travel through it. The grand era of spontaneous generation contained a vital seed of truth, a recognition that the universe has the capacity to create life. That seed, once discarded, has now grown into the entire, vibrant field of astrobiology, a quest to understand our own cosmic origins that began with a simple and not entirely foolish observation of the world. That same drive to explain our world's grandest features led to a theory as tangible as a piece of dried fruit. To understand why mountains thrust skyward and continents sprawled across the globe, 19th century, scientists looked at a simple, everyday process. They imagined a young Earth born molten and white-hot, slowly radiating its internal fire out into the cold of space. As it cooled, they reasoned, the entire planet would contract. And the solid crust, the outer skin of this shrinking sphere, would have no choice but to crumple and fold, just like the skin of an apple as its moist interior dries out. These wrinkles, they proposed, became our great mountain ranges. This was the shrinking Earth theory, an elegant and powerfully intuitive explanation for the planet's most dramatic geology. It made perfect sense with the knowledge of the time. Figures like the American geologist James Dana saw the Earth not as a static museum piece, but as an active, evolving body with a dramatic thermal history. They were correct in their fundamental premise: the planet was undergoing immense global-scale change. They were just wrong about the engine driving it. The theory began to fall apart as evidence mounted. If the entire planet was uniformly contracting, mountain building should be random, scattered across the globe. Instead, mountains clearly formed in long, linear chains, like the Great Spines of the Americas or the Himalayas. Even more damning, calculations showed that the amount of cooling required to create all the wrinkles on Earth would have been far more extreme than the geologic record allowed. The shrinking apple was a beautiful analogy, but it could not bear the weight of the data. The theory was abandoned, another dead end in our understanding of the world. Yet its ghost lived on in a crucial way. The shrinking Earth theory established the vital idea that planets are dynamic, that their surfaces are battlefields of titanic forces. It prepared the scientific mind to think on a global scale. When the true answer finally emerged, it was not a planet shriveling in on itself, but one whose skin is broken into giant plates, rafting on a churning, molten interior. Plate tectonics revealed a world of continental collisions and oceanic rifts, a machine driven by internal heat, not the loss of it. The wrinkle was replaced by the collision. But the core insight, that of a living, changing planet, was the shrinking Earth theory's greatest legacy. This principle of planetary transformation now guides our view of other worlds. We see the vast uplifted highlands of Venus, the solar system's largest volcano on Mars, and the cracked, icy surface of Jupiter's moon Europa, all testaments to worlds in constant, dramatic flux. The theory itself may have withered, but the seed it planted, the vision of a world that is truly alive, grew into a fundamental truth of our solar system. The elegance of a cosmic system forming from a mere cloud of gas and dust was too beautiful for some to accept. In the 18th century, two brilliant minds, Immanuel Kant and later Pierre-Simon Laplace, independently proposed a radical new origin story for our solar system. They envisioned a vast, slowly rotating nebula, a cloud of gas and dust gradually collapsing under its own gravity. As it contracted, it spun faster, flinging out a disk of material from which the planets could coalesce. It was a vision of serene, clockwork creation, a solar system born from orderly physical laws rather than celestial chaos. Yet this elegant model was soon cast aside. The 19th century favored drama over elegance, turning to catastrophic theories that involved a near miss or even a direct collision between our sun and another star. Such a violent encounter, it was thought, could have ripped out the raw material for planets, explaining their orbits in one spectacular event. The nebular hypothesis seemed to have fatal flaws. Critics pointed to the angular momentum problem. How could the Sun, which holds 99% of the solar system's mass, be spinning so slowly, while the tiny planets carry so much of the system's spin? It did not add up, and the quiet, graceful birth proposed by Kant and Laplace was abandoned for a more thrilling, explosive beginning. This rejection, however, was not the end of the story. The catastrophic model had its own insurmountable problems, primarily that such a stellar encounter is astronomically improbable. The stage was set for a triumphant return. With the dawn of the 20th century and the power of new computational tools, astronomers revisited the old idea. They discovered that the young sun could have transferred its angular momentum to the protoplanetary disk through powerful magnetic fields, effectively breaking its own spin while allowing the planets to form with their observed velocities. The perceived dynamical problems were not flaws in the original insight, but limitations in the mathematical tools of the past. The nebular hypothesis, once a discarded relic, is now the universally accepted foundation for how solar systems form, a process we can see in action around other young stars. This cycle of acceptance, rejection, and ultimate validation is a profound lesson in scientific humility. It reminds us that an elegant idea, even one ahead of its time, should never be buried forever, but kept in the vault of possibilities, waiting for the moment when new evidence or new understanding can reveal the truth that was there all along. Those tantalizing hints of green on Mars were not just lines on a map, but colors in a spectrum. As telescopes improved, a new hope emerged from the science of spectroscopy, the art of dissecting light to reveal the chemical fingerprints of distant worlds. Some astronomers, analyzing the faint light reflected from the Martian surface, believed they detected a signature eerily similar to chlorophyll, the very pigment that makes plant life on Earth green. It was a breathtaking proposition. The red planet was not a dead desert, but a world perhaps covered in hardy, widespread vegetation that changed with the seasons. The Martian canals might have been an illusion, but this was data. It felt like the first direct evidence that we were not alone, that another world was truly alive. This dream of Martian greenery collapsed under closer scrutiny. The spectral signals were not from organic matter, but from the specific way common minerals, like certain iron oxides and rocky silicates, reflected light under the thin, dry Martian atmosphere. What seemed like a biological signature was merely a geological one, a trick of the light played across millions of miles of empty space. It was a profound lesson in the perils of remote sensing, a cautionary tale about seeing what we desperately wanted to see in the data. Yet this failure was not an ending. It was a rigorous training ground. The very act of debunking the Martian chlorophyll myth forced scientists to become far more sophisticated. They had to learn to distinguish between the subtle spectral whispers of life and the loud echoes of non-living chemistry. They had to account for the distorting effects of a planet's atmosphere, its temperature, and even the angle of its sun. The techniques honed in the disappointment over Mars are the exact same tools we use today with spectacular success, not on planets in our own backyard, but on worlds orbiting distant stars. When our space telescopes like James Webb stare at the atmosphere of an exoplanet, they are looking for the faint, telltale dips in starlight that reveal the presence of gases like oxygen and methane, gases that on Earth are produced and replenished by life. The search for the chlorophyll of Mars was a false alarm, but it calibrated our instruments for a hunt far grander in scope. That abandoned hope for a green Mars taught us how to ask a better question, one we are now, for the first time in history, equipped to answer across the cosmic ocean. The red planet's spectral ghosts taught us to refine our search for life, but some questions probe far deeper than biology, reaching for the very origin and end of all things. For thousands of years, the concept of a universe with no beginning and no end felt profoundly right. Ancient Hindu cosmology described a cosmic breath, an endless rhythm of creation, preservation, and dissolution, with each cycle lasting billions of years. Greek Stoic philosophers envisioned a great year, a vast epoch after which the cosmos would be consumed by fire and reborn anew, repeating forever. This eternal, cyclic universe was a grand, comforting alternative to the intimidating notion of a single, definitive genesis from nothing. It stood in stark opposition to the 20th century's most triumphant discovery, the Big Bang, which pointed toward one explosive beginning. The evidence for that hot, dense origin is overwhelming, from the cosmic microwave background radiation to the abundance of light elements. Yet the ghost of the eternal cycle was not so easily banished. It has returned in the language of advanced mathematics and theoretical physics. Sir Roger Penrose's conformal cyclic cosmology, for instance, proposes a breathtaking vision where the end of our universe, stretched into a state of maximum emptiness, becomes mathematically identical to a new Big Bang, birthing the next cycle in an infinite series. Other models explore an oscillating universe, expanding from a Big Bang only to eventually collapse back in a big crunch, then rebound again forever. These are not ancient myths but sophisticated attempts to answer the most profound question the Big Bang leaves open: what, if anything, came before? Thinkers like Friedrich Nietzsche grappled with this conceptually through his idea of eternal recurrence, a philosophical proposition that all events would repeat themselves infinitely in an endless loop of time. While the evidence for our current expanding universe is undeniable, its ultimate fate is not. The discovery of dark energy and the accelerating expansion complicates the simple oscillating model, as a universe that flies apart forever may never collapse to begin the cycle anew. The cyclic universe idea, in its modern forms, remains unproven, a speculative frontier, but its enduring power lies in its ambition. It represents humanity's oldest and most persistent fascination, the desire to see our cosmos not as a lonely, one-time event, but as part of an eternal, grander pattern. This ancient intuition, once abandoned for a singular beginning, continues to whisper to our physicists, challenging them to look beyond the horizon of our own universe's birth. Our own solar system bears the scars of a forgotten war. The moon's cratered highlands and the ancient basins of Mercury stand as silent testimony to a period of unimaginable violence known as the Late Heavy Bombardment, a time when asteroids rained down across the inner planets. To explain this celestial onslaught, scientists proposed a phantom culprit, a fifth rocky world they called Planet V. This hypothetical planet, they suggested, once orbited peacefully between Mars and the asteroid belt until some gravitational nudge sent it spiraling into chaos. Its death throes would have gravitationally kicked a vast swarm of asteroids inward toward Earth and its neighbors in a cataclysm that reshaped young worlds. For a time, Planet V was an elegant solution to a prehistoric mystery. Yet, as computer models grew more sophisticated, the specific orbit of Planet V became difficult to justify. The beautiful, simple story of a single doomed world began to fray at the edges, and the hypothesis was gradually set aside. But the ghost of Planet V achieved something far more important than its own existence ever could. Its proposal forced astronomers to take the idea of planetary migration seriously, to simulate the solar system's infancy not as a stable clockwork but as a chaotic pinball machine. This line of inquiry led directly to the groundbreaking NICE model, which describes how the giant planets Jupiter, Saturn, Uranus, and Neptune slowly drifted from their original orbits. This grand migration would have destabilized the entire outer solar system, flinging comets and asteroids into the inner reaches and perfectly explaining the bombardment evidence. The search for a single lost planet revealed a much deeper truth, that entire worlds can wander, and that the gentle gravitational hand of a giant like Jupiter can sculpt and sometimes devastate the entire planetary family around it. The theory of Planet V was wrong in its details, but it was profoundly right in its spirit, teaching us that our cosmic neighborhood was forged not in tranquility, but in a tempest of dynamic instability. The violent chaos of the early solar system forces us to confront the raw, mindless physics that built our world. Yet from that same cosmic forge comes a question that stands in stark contrast to the clatter of colliding rocks. What if mind, in some elementary form, was there from the very beginning? This is the radical proposition of panpsychism, the idea that consciousness is not a late arrival in cosmic history but a fundamental feature of reality, as basic as mass or charge. Early thinkers like astronomer Arthur Eddington wrestled with this. He saw that physics describes the structure of the universe with exquisite mathematical detail, but it says nothing about the intrinsic nature of the stuff that has that structure. The electric charge of an electron is described perfectly by its equations, but what is the electron, in and of itself? Eddington and others speculated that perhaps the inner nature of matter is not inert, but involves some primitive form of experience or proto-consciousness. This was not a call for atoms to think, but for a universe where mind and matter are not two separate substances, but different aspects of a single, deeper reality. The theory was and remains firmly on the fringes of science. It cannot be tested with our current tools, and it seems to defy any attempt at a clear, falsifiable experiment. It was an idea that had to be abandoned by a science striving for objective, repeatable results. Yet, faint echoes of its central mystery resonate in one of the most successful and bizarre theories ever devised, quantum mechanics. In the strange world of the quantum, the act of observation appears to play a crucial role. The The famous thought experiment of Schrödinger's cat highlights the paradox, a cat that is simultaneously alive and dead until someone looks inside the box and forces reality to choose a single state. Mainstream physics explains this through decoherence, not a conscious observer. Yet, the very fact that the role of measurement is such a deep and unresolved problem in quantum theory forces us to confront the uncomfortable relationship between the world out there and our perception of it here. Panpsychism takes this a step further, suggesting that perhaps the observer effect is not a human peculiarity, but a fundamental feature of a universe where consciousness is not an emergent anomaly, but a basic property woven into the fabric of spacetime. It challenges the purely materialist view that consciousness is merely a byproduct of complex computation in the brain, an accidental ghost in the machine. If even a fraction of this abandoned idea holds a grain of truth, it would mean the cosmos is not a cold, empty void dotted with isolated pockets of awareness. It would be a universe in a state of becoming, a vast, interconnected network where every particle holds a faint spark of interiority, and our own rich inner lives are not separate from the cosmos, but a more complex and concentrated expression of its most fundamental nature. The Moon's origin story once centered on a cosmic spin cycle. Before scientists envisioned a colossal impact, they looked to the physics of a young, molten Earth spinning with ferocious speed. The idea was that this primordial planet, a seething ball of magma, rotated so rapidly that it began to bulge at its equator, eventually flinging off a gigantic blob of its own material. This ejected material, the theory proposed, coalesced in orbit to become our Moon. This was the Fission theory, and its most prominent champion was a scientist with a legendary name, George Darwin, son of the great naturalist Charles. He calculated and argued that the Pacific Ocean basin might even be the scar left behind from this violent birth. It was an elegant, almost poetic vision of our world literally giving birth to its companion. The theory, however, could not survive the harsh light of physics. The math simply did not work out. For Earth to have spun fast enough to throw off the Moon, it would have needed an impossibly short day, lasting only about 2 hours. Furthermore, no one could explain where all that tremendous rotational energy would have gone after the fission event. The mechanism was fatally flawed, and the fission theory was set aside as another beautiful, failed idea. Yet its core intuition was prophetic. George Darwin and his colleagues were absolutely right that Earth and the Moon share an intimate genetic bond. The fission theory correctly insisted that the Moon was made from the Earth itself, a concept that would prove to be its most vital legacy. Decades later, when the giant impact hypothesis emerged as the leading model, it incorporated this very insight. The new theory proposed that a Mars-sized body named Theia struck the young Earth, vaporizing and launching a massive ring of debris into space, debris that was predominantly made from Earth's own mantle. This perfectly explained the stunning geological evidence that Apollo astronauts later brought home. Rocks that showed the Moon and Earth's mantle have nearly identical compositions. The fission theory was wrong about the how, but it was brilliantly right about the what. It was the crucial stepping stone, the flawed but necessary guess that kept the scientific community focused on a shared origin, guiding them ultimately to a truth far more violent and wondrous than a simple spin. The universe does not require a single, dramatic birth. This was the bold challenge posed by the steady-state theory, a sophisticated and elegant alternative to the cataclysmic Big Bang. Its proponents, including the brilliant and often combative astronomer Fred Hoyle, envisioned a cosmos with no beginning and no end, an eternal, expanding entity that looked the same at all times from every vantage point. But how could this be possible if the universe was constantly stretching, thinning out the matter within it? The answer was a radical and subtle proposition: the continuous creation of matter. In the steady-state model, new hydrogen atoms were thought to pop into existence out of nothing, filling the void left by expansion and maintaining a perfectly constant density throughout all of time. It was a universe that simply always was, a serene and infinite ocean, self-renewing and eternal. This beautiful idea, however, met its end with a faint, static hiss. The accidental discovery of the cosmic microwave background radiation, a uniform glow bathing the entire cosmos, was the smoking gun. This was the cooled and stretched remnant of the universe's hot, dense infancy, a relic the steady-state model could not explain. The theory was overwhelmingly disproven, and the Big Bang became the standard model of cosmology. Yet, to dismiss the steady state as a mere failure is to miss its profound influence. Fred Hoyle, even as he argued against the Big Bang, made monumental contributions to our understanding of it. His work on nucleosynthesis revealed how stars forge the heavier elements that make up our world, a process that happens within the very framework he sought to challenge. And in a strange twist, the ghost of continuous creation did not vanish. It simply transformed. In the speculative realms of inflationary cosmology, our entire universe might be just one expanding bubble in a vast, eternally inflating multiverse. In this grander picture, new universe bubbles may be continuously spawning from the inflationary background, a process that echoes the steady state's vision of eternal, ongoing genesis on a far vaster scale. The steady-state theory was wrong, but its philosophical elegance and its power to provoke forced the Big Bang proponents to sharpen their evidence and refine their arguments. It stands as a powerful testament to the fact that in science, a beautiful, compelling, and ultimately incorrect idea can be just as vital to progress as the correct one, for it pushes us to prove our truths beyond any reasonable doubt. The human eye is a pattern-seeking machine, forever trying to assemble meaning from the chaos of shadows. When early astronomers trained their telescopes on Mars, they saw more than just indistinct smudges of red and ochre. They saw shifting, creeping patches of darkness that some observers whimsically named the blue scorpions. These were not literal creatures, but the name captured the uncanny sense that something was moving, perhaps even migrating across the Martian plains with the turning of the seasons. It was a compelling narrative, a story of life persisting on a harsh world, and it fueled the early dreams of exobiology. The truth, when it finally came from sharper lenses and orbital spacecraft, was both simpler and more majestic. The blue scorpions were not life. They were the breath of the planet itself, vast seasonal dust storms that swept across the basins, darkening regions as they passed, and the subtle shifting of surface albedo as thin layers of dust were scoured away by the wind or deposited elsewhere. The patterns were real, but their cause was the relentless, abiotic geology of a desert world. This misidentification, however, was far from a failure. It forced a crucial evolution in scientific thinking. Astronomers realized they needed a much stricter set of rules to tell the difference between a geological process and a potential biological signature. They had to learn to mistrust their own intuition, to build protocols that separated hope from evidence. This lesson is more vital today than ever before. As we peer at the hydrocarbon lakes of Saturn's moon Titan or the fractured, icy crust of Jupiter's moon Europa, we are once again faced with landscapes that defy our earthly expectations. Strange shapes, unexplained spectral signals, and enigmatic surface features will certainly challenge our interpretations. The ghost of the blue scorpions reminds us to be vigilant, to question the stories our minds are so eager to tell, and to remember that the universe is full of wonders that require no life to be profoundly, breathtakingly alien. Gravity may be the great architect of the cosmos, but it is not the only force at work in the void. For a time, a rival vision of the universe challenged this singular focus, one where invisible lines of magnetic force sculpted galaxies and lit the stars. Plasma cosmology proposed that electromagnetism, not just gravity, held the true blueprint for the large-scale structure of everything we see. Its proponents saw the cosmos not as a collection of isolated islands, but as a single, connected circuit, a web of electric currents flowing through the conductive medium of space itself. This was an electromagnetic universe alive with energy. The theory struggled to explain the foundational evidence for the Big Bang, particularly the perfect thermal echo of the cosmic microwave background, and it was ultimately sidelined by the prevailing gravitational model. Yet, to dismiss it entirely would be to ignore the brilliant light it shed in the darkness. The Nobel Prize-winning work of Hans Alfvén, a champion of this view, gave us the science of magnetohydrodynamics, the study of how magnetic fields can control the behavior of superheated, electrically charged gases or plasma. This is not just abstract theory, it is the operating manual for our own neighborhood. We now know that the space between the planets is not an empty vacuum, but a sea of plasma, the solar wind, which carries the sun's magnetic field out into a vast bubble called the heliosphere. Alfvén's insights are why we can predict the solar storms that threaten our satellites and power grids. They explain the magnificent arches of plasma that leap from the sun's surface and the shimmering curtains of the aurora at our poles. While plasma cosmology could not replace the standard model of the universe, it gifted us an entirely new way of seeing the local cosmos. It revealed that our solar system is a dynamic electrical environment, a place where magnetic forces paint the sky with light and govern the very space we travel through. This abandoned theory reminds us that the universe is a tapestry woven from many threads, and even the paths not taken can lead us to essential truths. For centuries, the heart of our own galaxy was a profound mystery hidden in plain sight. Gazing toward the constellation Sagittarius with optical telescopes, astronomers saw only a dark, murky void, a seemingly tranquil and empty region where they expected to find the galaxy's brilliant core. It was logical to assume the galactic center was a quiet, dormant place, perhaps just a dense cluster of old, faint stars. This view was a complete illusion. The truth was being concealed by vast, light-absorbing clouds of interstellar dust that blocked all visible light from ever reaching our eyes. Our own galaxy's heart was a secret kept from us by a cosmic curtain. The revolution came when we learned to see in new colors of light. With the birth of radio astronomy and later X-ray and infrared observatories, we could finally peer through the obscuring veil. What we found was not a quiet retirement home for stars, but a chaotic, violent maelstrom. At the very center sits Sagittarius, a star, a supermassive black hole with the weight of 4 million suns, a gravitational monster feasting on stray gas and dust. The space around it is a cosmic demolition derby, with stars whipping around at unimaginable speeds on frantic, slingshot orbits. The energy released in this frenzied activity creates a constant, high-energy hum across the electromagnetic spectrum, a roar we were completely deaf to for most of human history. The galactic center is not quiet, it is the engine room of the entire Milky Way. This dramatic shift in understanding holds a critical lesson that extends far beyond our own spiral home. It demonstrates that our entire conception of a cosmic object is limited by the narrow slice of reality our instruments can perceive. What we label as an abandoned or inactive region might simply be a place whose language we have not yet learned to hear. As we now turn our advanced telescopes toward the centers of other galaxies, we must remember the lesson of Sagittarius, a star, A galaxy that looks quiescent and peaceful in one type of light might be hiding a ferocious, energetic heart in another. The universe is always speaking, but are we listening on the right frequency? That same impulse to find order in the heavens once produced a simple mathematical sequence, a code that seemed to unlock the very architecture of our solar system. It was called the Titius-Bode law, and for a brief, glorious period, it appeared to be a fundamental rule written into the cosmos. The law was not derived from complex physics, but from a simple numerical pattern. You started with 0, then 3, then 6, 12, and so on, doubling each time. Adding 4 to each number and dividing by 10 gave a sequence that almost perfectly matched the average distances of the planets from the Sun, measured in astronomical units. Mercury at 0.4, Venus at 0.7, Earth at 1, Mars at 1.6. It even predicted the great gap between Mars and Jupiter, a space where the pattern insisted a planet should be. This led directly to the discovery of the asteroid series, the first and largest of the countless rocky bodies in that very belt. The law was hailed as a triumph of human reason, a key to divine design. Then came Neptune, when astronomers went looking for the planet causing gravitational perturbations in Uranus's orbit. The Titius-Bode law predicted where it should be. But when they found it, Neptune was far closer to the Sun than the sequence dictated. The pattern was broken. The law, which had seemed so elegant and universal, was suddenly revealed as nothing more than a curious coincidence, a numerical fluke. It was promptly abandoned as a true physical law of nature, yet its ghost has never fully departed. The fact that it worked so well for the inner solar system was not pure luck. It pointed toward the underlying processes that sculpted our planetary system in its youth. The spacing of the planets appears to be the result of dynamical forces like orbital resonances, where the gravitational pull between forming planets creates stable, repeating rhythms, pushing them into orderly orbits. The grand migration of the giant planets, as described by the NICE model, would have further sculpted these distances. The Titius-Bode sequence was a rough, empirical echo of this complex gravitational symphony. Its greatest legacy was not as a law but as a guide. It gave astronomers a specific place to look, a celestial hunting ground that proved incredibly fruitful. This abandoned rule stands as a permanent lesson in the scientific quest. It teaches us the vital difference between noticing a pattern and understanding the physical mechanism that creates it. We are pattern-seeking creatures, and sometimes the patterns we find are real, even if our first explanation for them is completely wrong. The romantic allure of a lost world has always captivated our storytelling instincts. In the 19th century, the puzzling gap between Mars and Jupiter seemed to demand a dramatic explanation, and astronomers provided one, a shattered planet they named Phaeton. The asteroid belt, according to this popular theory, was not a collection of small rocks, but the tragic debris of a full-sized world that met a violent, cataclysmic end. Perhaps it was torn apart by a colossal impact, or maybe it was ripped asunder by the immense gravitational forces of a nearby giant. This narrative gave the solar system a poignant history, a story of creation and destruction written in the rubble. It was a powerful, human-centered story that made the cold mechanics of planetary orbits feel deeply personal and thrilling. The hunt for asteroids fueled by this myth became a search for the tombstones of a lost civilization. We now know the truth is both less dramatic and more profound. The asteroids are not the pieces of a broken planet, but the leftover building blocks of one primordial material that never managed to coalesce. Jupiter's gravity, that colossal king of the planets, stirred the protoplanetary disk in that region with such violence that the infant planetesimals could never peacefully merge. They were doomed to forever collide and shatter, never achieving planetary unity. Yet, the Phaeton theory was not a complete failure. Its core intuition that planetary systems are arenas of immense violence and gravitational tyranny was absolutely correct. We see this principle playing out across the galaxy in the exotic exoplanetary systems we are now discovering. We find planets spiraling into their stars, others being flung into the interstellar void, and entire belts of debris that speak of past collisions and chaotic migrations. The story of Phaeton was a myth, but it correctly foreshadowed a universal truth that the formation of a solar system is not a gentle process, but a gravitational battlefield where worlds are made, broken, and forever reshaped by the most powerful forces in their neighborhood. Our moon was once thought to be a world of whispers and faint breaths. For centuries, skilled astronomers reported fleeting glows and shifting hazes on its surface, phenomena they called transient lunar events. These observations painted a picture of a world that was not entirely dead, a place with a wispy atmosphere and perhaps even the occasional puff of volcanic activity. It was a moon that felt closer, more dynamic, a celestial neighbor that still harbored secrets just beneath its dusty skin. This vision, however beautiful, was an illusion born from the limits of our own atmosphere. The shimmering air of Earth was distorting the view, turning tricks of the light into evidence of a living world. When robotic probes and the Apollo astronauts finally arrived, they found a reality far more stark and magnificent. The moon was an airless desert, its silence absolute, its surface a museum of ancient impacts preserved in perfect vacuum. The volcanic fires had been extinguished for billions of years. Yet this correction was not an end to the mystery, but a transformation of it. The very search for that lost lunar atmosphere, the hunt for those ghostly volcanic plumes, had forced us to look more carefully. It drove the development of sensitive instruments and the meticulous mapping of the lunar surface, a scientific groundwork that made the Apollo landings possible. And in a stunning twist, the modern legacy of that abandoned theory is not nothingness but ice. The same careful observation that debunked a thin atmosphere later revealed the presence of water ice, hiding in the permanent shadows of polar craters where the sun never shines. These frozen deposits are the treasure the old astronomers never knew they were seeking, a resource that could one day support human outposts and turn the moon from a destination into a gateway. The theory of an active moon was wrong, but the curiosity it ignited launched us toward our satellite, and that journey ultimately revealed a world with a complex and dramatic geological history, a world that now calls to us not for its whispers but for its water. Earth's story is deeply woven into the fabric of the galaxy itself. Long before we mapped the Milky Way, ancient astrologers and philosophers intuited a grand celestial rhythm, a cosmic year defined by our solar system's slow, 250 million-year journey around the galactic center. In these early systems, this immense orbit was thought to bring seasonal shifts to life on Earth, with each passage through a different galactic region ushering in epochs of creation and destruction. There is no evidence that the galaxy directly whispers to our biology in this mystical way, yet this poetic idea of a connected cosmos was asking a question far ahead of its time. Modern science is now discovering that our galactic address does indeed matter. As our solar system journeys around the Milky Way, it does not travel a smooth, empty path. It oscillates up and down through the galactic plane, and most significantly, periodically passes through the dense, turbulent spiral arms. These are not just collections of bright stars, they are regions of intense radiation and gravitational disturbance. When we traverse one of these arms, the increased density of stars and gas can gravitationally jostle the vast reservoir of icy bodies in the distant Oort cloud, sending a hail of comets inward toward the Sun. Some scientists now investigate whether these comet showers, triggered by the solar system's galactic orbit, could be linked to mass extinction events in Earth's deep past. Furthermore, the higher flux of cosmic rays in these regions could potentially influence our planet's climate by seeding cloud formation or directly impacting the biosphere. The abandoned concept of a cosmic year was wrong in its mechanism, but it was profoundly right in its scale. It correctly sensed that our planet is not an isolated ship, but a passenger on a much larger voyage, subject to the currents and weather of the galactic ocean. This perspective is now a cornerstone of astrobiology, forcing us to consider that the rise and fall of life on any world might be written not just in its own rocks, but in the silent, turning arms of its home galaxy. The continents hold a secret in their shapes, a jigsaw puzzle written across the ocean floor. For decades, the uncanny fit between South America and Africa was a geological riddle with no satisfying answer. Without the framework of plate tectonics, one bold and deeply intuitive idea emerged to explain it. Perhaps the planet itself was slowly inflating. The expanding Earth hypothesis proposed that our world was once a smaller sphere, its continents forming a complete, unbroken shell. As the planet expanded over billions of years, this shell cracked and the fragments drifted apart, creating the oceans in the widening gaps between them. It was a beautifully simple vision, a cosmic balloon whose skin was slowly stretching. The theory forced geologists to look at the entire globe as a single system, to take the matching coastlines and fossil records seriously as evidence of a planet in motion. It demanded a mechanism, any mechanism, to explain how continents could move, yet for all its elegance, the expansion could not withstand the evidence. Precise satellite measurements showed the Earth's radius was not increasing. More critically, the hypothesis could not explain the new discoveries on the ocean floor, the vast volcanic mountain ranges and deep trenches that pointed toward a different kind of engine entirely. The expanding Earth was a dead end, but its ghost was essential. By insisting that the continents had moved, it kept a radical idea alive in the face of staunch opposition. It was part of the fierce, contentious debate that forced the scientific community to eventually accept the true answer: plate tectonics. We now know the continents are not drifting apart on an expanding balloon, but rafting on giant, shifting plates, recycled in a continuous, slow-motion dance of creation and destruction at the mid-ocean ridges and deep-sea trenches. The expanding Earth was wrong, but its greatest legacy was its stubborn refusal to accept a static world. It served as a vital catalyst, a necessary provocation that helped break a scientific stalemate and clear the path for one of the most profound revolutions in our understanding of the planet we call home. This messy, fascinating history reveals a profound truth about how science actually works. We often picture it as a straight line from ignorance to truth, a simple march where old, wrong ideas are left behind forever. But the real story is far more human and far more interesting. A theory is rarely thrown out like a piece of garbage. It is more like a ship being dismantled for parts in a storm. When a beautiful idea like the Luminiferous Aether or the Martian Canals fails a crucial test, the scientific community does not simply forget it ever existed. They salvage its most valuable components. They take the rigorous methods it inspired, the new questions it raised, and the powerful metaphors it created. These pieces become the building blocks for the next, better theory. The concept of planetary migration, first dreamed up to explain a lost world like Planet V, was a salvaged part that later powered the revolutionary NICE model. The discarded cosmological constant was a forgotten tool that was perfectly suited, decades later, for unlocking the mystery of dark energy. This is not a story of being right or wrong. It is a story of a continuous, often chaotic conversation between our boldest imaginations and the stubborn, unyielding evidence of the real world. Recognizing this pattern does more than just give us a better history lesson. It changes how we view the cutting edge of science today. It asks us to be humble. Our most cherished modern theories about dark matter, the multiverse, or the nature of consciousness are our best current maps. But they are still just maps. Some of their details will inevitably be proven wrong, and some of the ideas we dismiss today as fringe or impossible might just be waiting for their moment, holding a piece of the puzzle we do not yet know we are missing. The greatest scientific breakthroughs often begin not with a confident answer, but with a respectful glance into the past, at the graveyard of abandoned ideas, wondering if we might have buried something vital there after all. Our journey through these 25 forgotten paths reveals that the history of science is not a graveyard of dead ideas, but a workshop of perpetual revision. From the geocentric universe that taught us the importance of our own viewpoint, to the expanding Earth that dared to suggest our planet is dynamic, each discarded theory held a vital spark. That spark was not always a fact, but more often a powerful question, a new way of looking at the cosmos that refused to accept the current limits of understanding. These so-called failures were the necessary friction that sharpened our intellect, proving that being wrong is not the opposite of science. It is an essential part of its engine. No idea is ever truly wasted if it compels us to look deeper, to build a better instrument, or to question a fundamental assumption we never knew we had. As we point our telescopes toward the enigmatic hearts of distant galaxies and design probes for icy moons, we carry this legacy forward. The most profound lesson is not that we were right, but that we kept searching. The cosmos remains a vast ocean of unsolved mysteries, and it is entirely possible that among today's most speculative, even dismissed, ideas about dark matter, cosmic consciousness, or the multiverse, we will find the foundational truths of tomorrow. Our greatest discoveries may not lie ahead in the unknown, but waiting patiently in the archives of our own brilliant, beautiful mistakes.